Courtney, if you can, great timing. Okay, again, welcome everyone to today's session of the technical introduction or technical training on the Eguana Evolve residential battery energy storage product and its various form factors and battery chemistry. So without any further ado, just wanted to let everybody know right up front, this is being recorded. So if you've got any details that you'd like to review at a later date or time, Courtney will be sharing the link to the recorded version after the session is completed, and you'll have access to that. We will have everybody's microphones muted during the session just to eliminate some of the background noise. Please feel free to use the chat window to put any questions along the way, and I'll be sure to address each of them individually during a Q&A session at the end of the session. So without, I guess, any further ado, let me go ahead and get started here. Okay, so again, my name is Jay Zarghami. I'm Eguana's training and support manager, and my email is shown here on this screen. If you've got any questions about anything in particular that's not covered here after the fact, when you're watching the recorded session, please feel free to email me. I'll be glad to help you with any design considerations, any of the specs that aren't covered in the documentation on the website. Please feel free to reach out, and I'll help you with that, whether it's a design consideration, something special that you're working on that isn't covered in the manuals, or anything you know, that isn't covered here in this session either. I'd be glad to review that with you. So the Eguana residential battery energy storage product, the Evolve line of products. The training for installation is split up into several parts, well, a couple of parts. First of all, as a resource for everyone out there, our website product page has all of the manuals, quick start guides, certificate information, all of that certification information. That's all on our product web page. All of the graphics and images shown throughout today's presentation are taken from those product resource documents. And in order to try and keep some continuity between the training information and what's presented online. What I'm going to be covering today is more of an introduction to the product, to features and functions by component, looking at some design considerations for solar plus storage, both at the product and system level. We'll look at some basics of the installation, and then do a quick intro to startup and system commissioning. What's not going to be covered today during this session, but is covered either remotely with an individual designated training person from Eguana. We've got several around the country. The commissioning steps of your first system install will be covered either remotely or on-site by that Eguana tech. They'll be reviewing the hardware installation itself, sort of a QA review of that installation, be powering it up, and then guiding you through the EMC commissioning procedure. Some of the definitions that are used throughout today's presentation are shown here. I'm just going to read through them real quickly. Some of them you should know, and some of them may be new to you best. Of course, it's a battery energy storage system. PCS is a power control system. That's basically the power electronics within our battery product, the inverter and transformer, all the power electronics. The BMS, the battery management system, there is an integrated BMS with each battery module that's housed within our product. And the EMC, the energy management controller, is sort of the gateway, the eyes and ears and the brains of the whole system for full behind the meter visibility and control of the battery. The EMS, the Energy Management System, consists of the Energy Management Controller and the ATS switching components and all of the interconnections, all the terminal interconnections. PV, of course, is photovoltaic. ATS, automatic transfer switch. SLD, of course, a single line diagram. PKI, public key infrastructure. That's just a nomenclature that we use to refer to the security certificate that's in the infrastructure of accessing these devices, the EMCs, for configuring and commissioning them in the field. There's a high-level security component for these devices, as we anticipate that they will be, and they are certified for, and we anticipate that they will be adopted nationwide for virtual power plant program, for grid services programs, and with the access to those programs and compensation by the utilities, security for locking in commissioning profiles, et cetera, is set pretty high by the utilities. And so that standard has been set. That security certificate is specific to your installer device, the laptop that you'll use to commission the system, and assigned through your installer account. So that's a PKI. The CT is a current transformer. SOC state of charge, UID user identifier, basically like a MAC address or a serial number for the EMC itself. ECI is the Eguana communications interface, not necessarily required for installation or commissioning of these systems, but just be aware that there is a second level software tool that allows for greater access to the inverter for whether it's troubleshooting or settings changes and stuff like that. ARC is auto recovery mode. We'll get into the details of that in the coming slides. But basically, the Evolve platform allows for auto recovery of any significantly depleted battery modules without having to pull it off the wall to send it back to the manufacturer for recovery, or no need for a special external charging device to recover any critically depleted batteries. As long as there is grid voltage, the system will auto recover any battery modules that can be auto recovered or that can be recovered. Which is a really nice feature. The PDU is the power distribution unit, basically just a metering circuit within the EMC. It's got a built-in meter in there. So moving right along, product introduction. What we're going to be looking at here next is the Evolve system components, the system architecture for AC coupling, solar plus storage. We'll look at ATS and EMC functions. We'll look at the PCS architecture, basically the system layout, AC and DC interconnection. We'll look at the battery architecture, basically the DC or the battery cabinet connections real quickly, and touch on the LFP chemistry, highlights of that battery module option. We'll look at battery system protection functions and how they relate to the system overall. Again, all of the resources that are referenced throughout today's presentation can be found on the product webpage. That product webpage is listed here, eguanatech.com/product/evolve. I highly recommend you look at that webpage if you haven't already. The three main resources are listed here. The Evolve Hub installation manual, which covers overall system design and interconnection of critical components, including NEC required disconnects, etc. The Evolve LFP or ESS installation and startup manuals, those are both listed there for whichever product you end up installing. And the Evolve wiring and commissioning quick guide, which is really a good resource once you've already gone through the manuals, and to have a quick on-site reference. It's a simple 2-page quick guide. The first page is for the wiring, second page is for commissioning. Really good resources to make your installs go quickly and smoothly. Okay, the product platform is broken down into 4 major subgroups. As shown here, the monitoring consists of the consumer user interface, or the consumer monitor. Graphics shown here are from the consumer user interface. The consumer user interface is built up of these blocks that will reorient themselves and display similarly, just stacked based on the aspect ratio or the type of device that you're looking at it on. So it's a URL, so it's a web interface that whether you're looking at it on a desktop or on a tablet or on a smartphone, those graphics will look exactly the same. The blocks will just automatically reorient themselves, and you can scroll through them and see all of the same information displayed similarly. Monitoring also consists of the installer user interface, not shown here, but more of a utilitarian interface that allows you as the installer to onboard new devices, to make remote configuration changes, to add or delete your own additional users or devices as necessary. We also have some built-in fleet aggregator tools, as well as obviously account administration and remote configurability, as I just mentioned. The next major block is the EMS, or the energy management system. This takes care of the management and cloud reporting. So there's parallel communication pathways, either wired Ethernet or consumer Wi-Fi. Sorry about that. Put my phone on mute. So cloud communication access through the EMS or the EMC. It also controls PV and load curtailment controls, sending a messaging to the battery to do whatever it needs to, whether it's grid tied or in off-grid mode. There's best control via Modbus. So there's a serial Modbus connection from the EMC over to the battery to control battery charge discharge, as well as to pull for battery status information. There's system fault handling and reporting, as well as automatic transfer switch. The battery cabinets themselves are shown here on the right, these last 2 blocks. The PCS cabinet is the power control system, basically the inverter and other power electronics in there. Also acts as a battery gateway or bridge to the AC grid and the AC loads. The PCS ensures a safe operation of the battery and inverter and is rated at a 5 kVA per power. It does have quite a bit of surge capability. And that's detailed on the spec sheet that you can see online. It'll go up to 170% of nameplate rating, or 8.5 kVA for up to 5 seconds. It'll do 120% of nameplate rating, or about 6 kVA for up to 30 minutes. The DC component, the BMS and battery, what's shown here is from the ESS system. The LFP cabinet looks a little bit different. The batteries are just oriented differently inside the battery cabinet and are just interconnected slightly differently. Those differences are detailed in the installation manual. So please, if you've installed one and you're going to install the other, make sure that you take a look at that other manual. The DC cabinet consists of the battery management system and battery, obviously. The BMS ensures a safe operation of the battery by monitoring voltage, temperature, and other battery health metrics, and communicates that back to the inverter for charge and discharge ratings. Also housed within the DC cabinet is the battery disconnect. It's just basically a DC breaker, a kill switch inside here. The LFP system, the capacity ranges from the 14 kWh base system up to 42 kWh maximum, and the NMC or ESS version of the Evolve product is scalable from the base size of 13 kWh up to 39 kWh. A quick look at the Pylon Tech LFP battery modules. The LFP is a lithium iron phosphate. It's non-toxic, non-polluting, and environmentally friendly. Much higher percentage of recyclable materials within this this version of the product. Protection functions including over discharge, overcharge, overcurrent, kind of basic stuff for most batteries. It does have a flexible configuration. Multiple battery modules can be connected in parallel to extend capacity and power. So once you've installed a system, say a base system of 14 kWh, and the customer decides that they'd like to add more storage capacity, basically make that bucket bigger, you can come back later and bolt on another DC cabinet and not have to rewire another inverter and you know, run conduit and get new interconnection agreements and all of that stuff. So you can easily add capacity without changing your interconnection topology or your configuration. It does have a self cooling mode with reduced system noise. The module has less self-discharge or parasitic loads, and up to 6 months without charging is possible. It has an excellent performance characteristics of shallow charge and discharge. The working temperature range is important here. It goes from a -10 C to 50 C. So from pretty cold to pretty hot. You can do the math. For charging, it's from 0 C to 50 C, and discharging is from -C to +50 C, -10 C to +50 C. The warranty is based on a 6,000 full cycle life or 10-year warranty with an anticipated 15+ year design. And this is what it looks like when installed. The LFP battery cabinet is slightly larger than the inverter cabinet. Okay, a quick look or an introduction to AC coupling, solar, and storage. To most people by now, this is pretty basic stuff, but if you're new to batteries or to AC coupled batteries, if you've only done DC coupled batteries, then this is a quick intro to AC coupling. So just basically means that the PV, the loads, and the BESS, the battery, are all parallel connected to the home load center, functionally anyway. This is ideal for the retrofit market. And please note that there is no PV panel or PV module DC input to the battery system itself. All PV modules must have their own PV inverters, be they micro inverters or string inverters, doesn't really matter. The technical, I guess, conceptually, that's all connected in parallel. But you'll see in the coming slides where the interconnections are and how they are managed. Speaking of which, here we go. The AC coupling solar plus storage is controlled by the EMS, the Energy Management System, or the Evolve Hub, as shown here. And again, this diagram is taken directly from the Evolve Hub manual. This is figure 2 of the Evolve Hub and ESS solar plus storage. The CT measurements are how the hub or the EMC within the EMS knows what's happening behind the meter and is able to maintain net zero at the utility meter. So there's a set of mains or load CTs that are placed at the main service panel, measuring import and export to and from the grid. There's a CT measuring PV. Now, whether it's just PV that's going through the battery system or if it's extra PV, all of the PV needs to be measured in order to get a true net zero as much as the battery is able to charge, you know, to maintain that net zero. And then again, there's a battery CT that will give us feedback on whether or not the battery is doing what we've been telling it to do, to charge and discharge at a certain amount. And we get that battery monitoring information, and all that stuff is nicely displayed on the consumer user interface as well as on the installer user interface. That energy algorithm for solar self-consumption is pretty simple. The battery is told to charge whenever solar is greater than the load, and the battery is told to discharge whenever solar is less than the loads. The measurement, decision-making, and command cycle loop is 5 times per second. So it's pretty quick, real-time maintenance of flatline net zero at the meter. Unless there's more PV than more excess PV than what the battery is able to charge. And the battery can only charge or discharge while grid tied up to 5 kW. And if there's more than 5 kW excess PV, then any excess PV will be exported to the grid. Quick look at the system architecture of the Eguana AC battery and the Evolve Hub, which is the EMC and ATS in here, is laid out here in a simple sort of block diagram. And again, this graphic is from the Hub manual. This is the installation conduit plan for solar plus storage installation. The LFP base model is shown here. The base model meaning that it only has the one battery cabinet and a 14 kWh capacity. If this was a larger system, a 28 kWh, for example, you would just have a second battery cabinet mounted off to the right here. These disconnects, the load side and grid side disconnects between the Evolve Hub and the LFP are as per NEC 705 and 706, where both serving the need to disconnect any grid-tied inverters, which is 705, and then 706 for any non-grounded conductors coming to or from a battery also need to be run through visible lockable blade type disconnect. So those are shown there for a reason. Just the same as the PV disconnect, if you had a string inverter, that PV AC disconnect needs to be located at the inverter location. So these are all the simple interconnections. The sub panel, or the critical backup load sub panel, is going to be a new sub panel that needs to be installed, where you would put any selected essential loads and relocate them into that sub panel. So the cost of your installation, of course, is going to rely upon location of all of these system components, these balance of system materials or whatever. There's a single 40 amp interconnection at the main service panel. The benefit of the Evolve Hub is such that if you've maxed out, say if you've got a 200 amp service panel, and this, let's say that this string inverter is a SolarEdge 7600. That's the maximum that you can install into a 40 amp interconnection on the service panel. And one of the nice features is that the Evolve Hub will pass through up to a 40 amp circuit, or that 7600 watt PV inverter, while grid tied. Those loads will be served in the sub panel while grid tied or in off grid mode. Any excess PV is passed through the hub to this common connection. So if you were connecting that PV inverter, say was originally connected to that 40 amp breaker, you would then disconnect the PV from that 40 amp breaker, connect it through the new backup load sub panel, and then through the Evolve Hub, and then reuse that same 40 amp interconnection. The good thing about this Evolve Hub is that as per the 2020 NEC 705.13, I believe, PCS controls, the Evolve Hub monitors in real time, again, what the PV production is, and based on that PV, that level of PV generation, it controls or limits the battery's discharge to be whatever the PV is, plus the discharge never exceeds that 40 amps. So you could have this 5 kW grid tied battery inverter plus a 7600 watt SolarEdge inverter, for example, all connected through a single 40 amp breaker, which normally would completely exceed that rating. But because of the new NEC and the PCS controls through the Evolve Hub, that's a nice added benefit. So keep that in mind. Also keep in mind that if you are using that exact setup, SolarEdge 7600, you've got to have a way of curtailing that when you go to off-grid mode, because when we're in off-grid mode, because that battery inverter is only a 5 kW inverter, it will only charge up to 5 kW of excess PV. So this that SolarEdge 7600 has got to be derated down to 5 kW or maybe 5,700 watts nameplate rating, and that can be done through controls and a relay interface that we've got on our PCS, and then through the PRI, the power reduction interface on the SolarEdge inverter. Any other inverter choices you make necessarily need to be limited to a allow for no more than 5 kW of excess PV when in off-grid mode, because if you can't derate that inverter, then that excess current above 20.8 amps, or above the 5 kW power rating, will cause an overcurrent condition in off-grid mode and trip the whole system off, and those backup loads will no longer be served. The PCS will reset itself after a minute. Again, if that PV is overdriving the battery, it'll trip itself off again. It'll reset itself 3 times. These are nuisance trips, but after the 3rd time and it resets and sees that, it will go into a service mode and off-grid mode. And so if the customer's not home to reset that, none of those loads in the sub panel will be served, and really is just a poor execution of the installation. So please pay attention to all of the details that are listed in the Evolve Hub manual as far as sizing the PV circuit. It's very important and will help you to avoid any service headaches down the road. Okay, quick look at the battery architecture. This is just a brief look at the DC cabinet and some of the connections, both the DC conductor cabling and the communications cabling, and how that's laid out for a base system, or as shown here, for a base system, which is the 1 DC cabinet plus 1 extension cabinet. I won't go into the details here, but please note these details in the installation manual. Okay, quick look at some PCS built-in battery protection functions. The auto recovery feature, the batteries will go into a hibernation mode whenever they drop below a critical minimum SOC. If this does happen and you're on site as an installer, do not turn on the battery modules from the module power switch, because the PCS has controls to take that battery out of hibernation as long as there is grid voltage available. There's no need for external battery charging equipment, as I mentioned earlier in the presentation. There is, of course, a battery maintenance routine that's pretty standard for most systems. If any battery module SOC versus a battery rack SOC is greater than a 3% delta, the PCS will warn the controller to prioritize an automated SOC balancing routine following the end of the prior to use case cycle, like, charge or discharge because of PV. Little note here, PCS pre-charge circuit, just be informed that there is a pre-charge circuit within the inverter that prevents high inrush currents to the bulk capacitors whenever the battery power is applied. And when shut off, it reduces standby losses in sleep mode. So it's not really something that's required for installation, but just as a sort of a note, if you're turning a system off or on that's already running, if there's a pre-charge circuit in there that you should be aware of. I think there's a note in the manual as well. If you're to turn the DC breaker off, to wait a minute so that that pre-charge circuit can discharge before you turn it back on again. Okay, let's look at some system design considerations. What we're going to look at here in the next few slides are the PV to battery system ratios. We'll look at breaker sizing for your interconnection. Look at backup power, battery capacity sizing based on a nominal load, PCS output power limitations for both inrush as well as transient performance. We'll look at some typical home load profile examples and some notable home load cases as well for backup load planning. Really important there, and in this case, and this is a really important step, is planning your backup loads panel. And in planning that, you do need to make some, take some measurements. And when you do that, what equipment do you need in order to measure total black start load profile for that new backup loads panel? As with many things, and most importantly with planning a battery system that does provide backup services, some planning will pay you tenfold on the back end and avoided nuisance trips and truck rolls to do service calls if you overload that backup loads panel. Can't stress this enough, and we will go into a little bit of detail on that, as it is probably one of the most important steps when planning these installs. We'll also look at a single line diagram review, not really an in-depth review, but we'll do a quick look at the template, and again, it's referenced from the install manual. Okay, real quick, PV inverter to battery inverter ratios. As a general rule, it's 1-to-1. This allows the battery to absorb peak PV current until the battery is full, given that there are no off-grid loads. The battery charge is limited to 5 kW, and so that's the reasoning behind not wanting to overdrive the battery inverter in off-grid mode. And if you've got no way to derate that solar that's tied into the system that will be served when it goes into backup mode during a grid outage, if that can't be derated, as I mentioned with the Solar Edge inverter with the PRI interface on that inverter, then you must physically partition that PV array in order to not overdrive the PV that's attached to the backup loads panel. Again, the battery discharge has limited surge capability up to a maximum of 8.5 kW, or about 35 amps. And again, that's for about 5 seconds, that's the maximum. With caution, I hesitate to put this on here, but I did put it on here. The solar that's attached to the backup loads panel, with some caution, can be oversized on the nameplate rating to about 6 kW or 5,800 watts based on the array orientation, time of day, and baseline load. Again, the limitation is the excess PV generation. So if there's ever a chance of there being no backup loads, or maybe 100 watts of backup loads on a high efficiency load panel, and you've got more than 5,200 watts of generation, then that excess PV is going to be 5 kW or greater. You will trip the battery offline and none of those loads will be served. So again, with caution, a little bit of room to fudge that a little bit. So again, with that PV inverter to battery inverter ratio, when the PV to battery ratio is greater than 1-to-1, the PV, some of the PV is connected directly to the main panel when export is permitted. That excess PV, as I mentioned, as far as splitting up that array, that excess PV will not be a part of the backup loads panel and charging the battery when the grid is down. And again, as shown here, this little CT symbol here, that little circle, that is to stress that all of the PV needs to be measured while grid tied, not just the PV that's going to serve the backup loads when in off-grid mode. So we've got to measure all the PV while grid tied in order to maximize charging of the battery during normal operation. So, quick review, backup power. The Evolve system is rated for emergency backup power only. It is not intended for off-grid use exclusively. It is black start capable for both loads and solar PV, meaning that it goes from being a current source that is synchronized to the grid voltage to being a voltage source when the grid is down. Whole home backup is not possible without load management. So again, whole home backup is kind of a touchy phrase in the battery world, and you really take on the responsibility of the utility effectively when you're either doing an off-grid system or trying to do whole home backup without load management. So let's try and stay away from that and carefully select essential loads that will be put into a new backup loads panel. Again, proper planning pays dividends on the back end and will help to eliminate truck rolls, keep your customers happy, and get you more references. So, quick exercise or a question: what capacity do you reserve for the emergency backup power? Well, it depends. How long are your outages and what size are the loads? The limits of the PCS and backup mode for reference are shown here. The continuous power for a resistive load, purely resistive load, whether it's a toaster, oven, or whatever, that limit is 5 kVA at 240 volts, or 20.8 amps on either leg of the load circuit. It has a surge rating, again, 5-second surge rating maximum, up to 8.5 kVA, and 30 minutes up to 6 kVA. And that is split between the two legs. It has the ability to withstand a transient peak of 8 amps for 100 microseconds. We'll get into some of the details on that, on what types of loads cause transients. So typical home loads shown in this graphic here. Again, these different color-coded circles represent the continuous load, inrush load or motor load characteristics, and then the transient peak type load characteristics. Again, purely resistive loads like a toaster would fall completely within the blue circle and are easy to add when you're doing your backup loads panel planning. As far as some of your other home appliances, like a refrigerator, most especially, has a characteristic of a continuous load, which is kind of like it's running watts. And when that compressor cycles, it'll have characteristics of inrush. That compressor will have quite a bit of surge. It could be quite a bit more than what its running watts are, especially for today's energy efficient refrigerators. So, and then other home appliances or consumer electronics would have characteristics of both that continuous load profile as well as the transient. These switch mode power supplies do have transients that they introduce to the voltage waveform. And if they are to occur simultaneously, they have an additive effect and could trip the battery offline if it exceeds that 8 amp 100 microsecond limitation. CFLs, fluorescent lights in general, gas ignited lights fall completely within that transient load characteristic circle, the red circle here. And should absolutely be avoided if at all possible, because most people are not going to have the type of equipment to measure what those transients are in order to plan that backup load. So it's best to keep those to the bare minimum and or eliminate them whenever possible. To illustrate that point for backup load planning, measure to be sure. If the manufacturer, and in this case, this is from an O-scope measurement taken in the lab from a refrigerator our product manager had access to. Don't expect everyone to have an O-scope or a data scope in the field, but this is, again, just to illustrate the point that manufacturer's nameplate rating is shown here, where the manufacturer stated that the surge rating is only 3 times continuous. But in this case, as shown here, the surge was actually 10 times the continuous load. So whether that was an old refrigerator, needed servicing for some reason, whatever the case may be, looking at the manufacturer's nameplate is not going to serve you well in all cases. So again, measure to be sure. Well, if you don't have an O-scope, how are you going to do that? Same thing for the transient spikes. Standard ammeter isn't going to show how high those transients are, and if they're added, what that cumulative effect might be if it exceeds the withstand characteristics of the PCS. Again, consumer electronics, same thing. Those transient spikes, when those power supplies, those switch mode power supplies fire, are going to be could be troublesome, and you cannot read them using a standard ammeter. So how would you measure those different types of loads when you're doing your load planning? Again, because the backup loads panel measuring to be sure and planning that load panel is going to pay dividends. I have to stress this because this is the #1 cause for service calls for truck rolls after a battery system has been installed. So this is very important. Those continuous loads can easily be measured with a standard ammeter, but as most of you may well be aware, inrush characteristics and inrush measurement on an ammeter is a pretty common feature these days. And if you don't have one, you should definitely look into getting one, because that will not only measure the continuous, but will also measure peak and inrush current as required by a motor load and most common household appliances, you're going to need this to measure that. At least the ones that you're going to want to put on the backup loads panel. As far as consumer electronics with the switch mode power supply, there's really no way to measure transients, whether it's from those power supplies or from a gas ignited bulb. But the best way to mitigate any potential harmful effects of these consumer electronics is to put them all behind a standard home UPS, an uninterruptible power supply. Basically a home office UPS, you can pay anywhere from $100 to $300 or $400 for one, but $150 to $250 will get you a pretty decent UPS. And if you plug all of those devices into a power strip behind that UPS will have two benefits for that consumer. One is it will protect all those consumer electronics from any outage. So there's a transition of 4 seconds when the grid goes down before the evolved battery comes online. And it'll protect all of those consumer electronics from that 4-second power interruption. So they'll stay powered during that transition. It also has the added feature, the benefit of protecting the evolved battery from those transients. Those transient spikes are filtered out by the UPS and will help to avoid any nuisance trips when in off-grid mode, so keep that in mind. So quick summary then on backup power functionality. Backup power system is rated for 5 kW continuous. Black start of PV and all loads must take into account all limits, continuous, surge, and peak transient. If you can avoid the peak transient type loads, that's probably your best bet whenever possible. The others can be measured, and make note of the type of equipment that you'll need to do that. Again, the surge rating is 170% of nameplate peak for 5 seconds or 120% peak for 30 minutes. The home load profile may constrain the backup power limits due to a high quantity of nonlinear loads. And you got to make sure that you balance your loads on that backup loads panel between the phases, both L1 and L2. All right, that's all the boring, important stuff. Now going on to installation. Again, all of these graphics are taken from those 3 manuals, or the 2 manuals and the 1 quick start guide that I mentioned in the beginning of the presentation. This is the single line diagram as shown in the Evolve Hub manual. This can be used as a template for your permit plan sets for your electrical drawings, single line, the SLDs. And again, these required disconnects are shown here. NEC required disconnects. If your AHJ requires you to have a disconnect at the main panel location, then electrically, whether you put it here in front of the hub between the service panel and the hub, which will cut off your backup loads subpanel, or if you electrically locate it here, but just physically locate it by the main service panel, that's going to be in addition to the disconnects that are required at the inverter location. So please remember that. It will save you headaches when it comes time for inspection and for commissioning the system, as well as servicing it whenever necessary. The PV is shown here. Again, this AC rating or the DC is not within the scope of this SLD. All of this stuff, all of this information, this is shown in the install manual, in the hub install manual. So please give this a quick look and make sure that your designers, people who are putting your plan sets together, have this template. Okay, some basic considerations for installation. Some environmental considerations, of course, the temperature rating. Battery is rated from -10 to 50 degrees C. So if you're in a really cold area up in the mountains somewhere, you might want to consider putting it inside the garage. Of course, you don't want to have it in direct sunlight on a south-facing wall because if ambient temperatures, let's say, are 45 degrees, inside that battery cabinet, it will exceed that 50 degrees. So you want to make sure that you're on a north-facing wall or it's shaded, if not inside a garage or something like that. It is suitable for either indoor or outdoor installation. It's a NEMA type 3R enclosure. So it's outdoor rated, but it's also indoor approved. Again, do not install in direct sunlight. And that battery cabinet is convection cooling only. There are 2 fans in the PCS cabinet, but the battery cabinet is only has ambient convection cooling setup. Structural considerations: that the structure that you're mounting it to must support the weight of a wall-mounted system, because this is a wall-mounted system only. There is no floor mount option for this product as of yet. As far as wiring considerations, in addition to the AC power cabling, those power conductors, there are CTs that need to be wired from the EMS to the PCS to measure the battery, to the PV inside the backup load subpanel, as well as any other PV that's behind the meter, as well as a CT run out to the main service panel. So in order to minimize the cost of all of your materials, as well as the time to install it, locating the system as close to the main service panel whenever possible, whether it's on the same wall or on an opposing wall inside a garage, is usually your best bet for best practices, and efficient install. Keep in mind that the Evolve Hub backup load control relies on AK1 relay connection inside the PCS. That relay wiring is a simple plug and play two wire run, but it is provided with each system and is at a fixed length. And unless you want to end up doing extra wiring, locating the Evolve Hub itself within no more than about 2 feet to the left of the PCS, as shown in the installation guideline, is your best bet. It will save you on installation time. Again, read the manual, please read the manual. And then there's an EMC to PCS communications for serial Modbus or it's RS-45 connection for battery control. So pay close attention to the battery module connections, as I showed you in the DC architecture drawing. All of the LFP power conductor connections, as well as the communications connections, are very specific. So please pay attention to the instructions that are provided. Another quick look at the conduit plan. This is the same drawing that was up a few slides ago, with the associated suggested circuit designators and wire sizes. Again, this is up to your designer based on conductor length, overall conductor length, and wire fill of whatever else you might have in there. The CT pigtails, so the CT wire pairs that come with the CTs are a standard 8 feet long. And they will reach from the hub to the battery and to a sub panel, for example, if they are located adjacent to each other. But getting all of that to work, and then also having those 8-foot pigtails reach to the main service panel, is sometimes a challenge. So they can be extended, but you got to make sure that you use manufacturer spec wiring and splicing method when you do that. Those extensions can be up to 500 feet when done correctly, and those specs are given as well in the manual. Okay, so here's some screen captures from our install and commissioning quick guide. Let me show you what that whole thing looks like real quick here. So this is the quick guide, the install and commissioning quick guide. Page 1 is all the wiring interconnection with the hub shown here in the upper left, and interconnecting to the different components of the installation. Second page is the commissioning quick guide. I won't go into the commissioning quick guide, but that right there is basically the outline of that. I'm gonna go back to, wait, wrong one. Back to our presentation. So that's what these are taken from, this install and commissioning quick guide. The details are shown, for example, this is for the AK1 wiring, which is shown down in the lower middle section of the first page. The PCS cabinet You know it's a PCS cabinet because it's got the lights on the front of it. That circle shows the detail of where that AK1 relay terminal plug is located and the wiring that would then connect to the Evolve hub, the AK1 PCS plug inside the hub. All of the other interconnections are shown similarly with the detail that's blown up on the left, shown in the small circle where it's located. CT placement, for example, here, as shown for the batteries inside the PCS cabinet, the little triangles show the arrow in which those CT arrows need to face. That's the end of the installation. Once you've got everything installed, wired up, and CTs are landed properly, then it's just going to be a matter of powering everything up. Quick review of the power up sequence is similar to a string inverter. You want to turn the DC on first, then the AC. The one exception being the Evolve hub breaker at the main panel will supply grid voltage to the EMS and to the normally closed ATS contactors, which would then serve the backup loads panel. Because the battery system itself can be completely powered down with the disconnects, proper disconnects turned off. If that grid voltage is applied with the 40 amp breaker, it will pass through the hub ATS circuit and power that backup loads panel and the PV that's on it, as well as the loads. So turn on that Evolve hub breaker at the main panel as your first step. And then when it comes to turning on the battery system itself, you want to turn on all the power switches, all the toggle switches shown here with the blue arrow on each one of the modules. Once they're all powered on, then you press the red SW button shown with this red arrow here on the master battery module only. That's going to be the one in position number 1 on the lower front of the first DC cabinet. Once all the battery modules will each turn on, you'll see the LEDs come on all the battery modules. And if you've got all of your communications cables and power conductors wired correctly, all of the battery modules will turn on by pressing the red SW button on the first battery module. Once that's on, then you turn on the battery DC disconnector, that DC breaker inside the DC cabinet, and that powers on the battery inverter. Once that's powered on from the DC, then you turn on the battery AC disconnects, and a 5-minute grid connect timer starts up. Standard IEEE 1547 5-minute timer. Once that has elapsed and the grid voltage is within specs, the battery, the front panel of the PCS will have a solid blue light saying that it's in grid connected or gate block mode. At that point, then you would proceed to system commissioning. At this point in time, a direct connection to the controller with a field laptop is required, or if you've got a tablet with a USB plug accessory, then you can use a tablet as well, as long as that tablet has a browser, has the Chrome browser or similar on it. So looking at the system commissioning step, I'm just going to go some very basic bits of information here. We'll look at prerequisites, pre-commissioning requirements, and then the actual commissioning. Prerequisites, as I mentioned just now, are a web browser, of course. You'll need an internet connection so that that controller can connect to the cloud and download a list of your installer group's security certificates, which will allow system, controller configuration and final commissioning of the battery system. There is a USB to mini USB cable that's included with each system. And then the PKI certificate is something that you'll have to download onto that field laptop separately. That certificate is good for up to a year. After a year, you just have to download another one. You can issue those. Whoever the administrator is for your installer group will be the one to issue that certificate. And that's covered in the commissioning training, one-on-one with one of our technical specialists. So pre-commissioning, administrative, first time only, and it's specific to that device, as I was just mentioning. You would log into your installer account and you would get that PKI certificate and load it onto the laptop. Once that's done, then that laptop is ready to commission your battery system. Once you've got the EMC or the energy management system powered on, you would enter the Wi-Fi SSID and password if you're not using wired Ethernet. The EMC would report to the server, and it would download the list of certificates, as I just mentioned, of all of the approved installers who are allowed to access that device. That installer issued PKI certificate is presented to the EMC, and then access is granted to configure the system. As far as onboarding your device, you would record the device UID, which is given with each new system out of the box, as well as the customer name and address and email for monitoring. You would record all that stuff when you onboard the device. Then you would go into the configuration steps and follow the quick guide and put in whether it's self-supply, time of use, etc. Configure the CTs. There's an auto detect feature that's really nice that will automatically detect. It'll walk you through automatically detecting all of the CTs in the system, and based on that logic, will tell you if you've made any errors on placing the CTs, wiring the CTs, or if your phase wiring on your AC conductors has been reversed anywhere from the main service panel to where those CTs are, whether it's in the backup loads panel for the PV or the battery itself. Then the last step is just a quick calibration mode where you can calibrate the voltage and current for those CT measurements onto the PDU of the EMC, and then you're good to go. That's it. That's the end of the installation. Once you finish the calibration step, the system should be charging or discharging based on whatever the conditions are of the PV and the home loads. And the next step would be to do a backup loads test, kill main power, the main breaker, kill the power to main service panel, observe the battery has a 4-second delay, goes into off-grid mode, powers the backup loads panel. PV would then turn on in the backup loads panel 5 minutes later. You would see that the system is then working in an off-grid mode. Your customer would have a big smile on their face, and you go on to the next install, or go home for the day and have a beer if that's your thing. So anyways, that's it for today's presentation. I'm gonna go to the Q&A session now and go through these one by one. Let's see. Well, first off, thank you all for joining us today. I hope it was not too boring and presented some information that will help you in your company and installing these battery systems. So again, this session today has been recorded and it will be available to you after the session is complete or sometime later today. Let's see. From Tafara, is it correct to say the Evolve Hub is basically a battery inverter? No, the Evolve Hub is like a gateway. It's an energy management system. The hub is the energy management system that connects the actual battery system, which is the ESS or the LFP AC battery. It connects that to the grid. It connects the backup loads panel and the PV to the grid, and it is the hub for communications and control and monitoring of the whole system, behind the meter visibility and control of the battery. So the hub itself is not the battery inverter. The battery inverter is in the Evolve LFP or the Evolve ESS part of the product. Let me pull that up here. Let's see here. Boom. Okay. On this slide here, if you look at this, Tafara, the Evolve Hub is the smaller enclosure in the middle. That is the gateway that provides monitoring via CTs and communications interface with the battery. It measures PV generation, it measures home loads, and it communicates with the battery to tell it to charge and discharge. The battery inverter is located within the PCS cabinet of the Evolve LFP in this case, and the hub itself just provides monitoring and control and communications. Andra, I hope that answers your question as well. The hub is more of a control. There's a separate inverter for the battery, right? Yes, you're correct. SOC is state of charge. That was covered in the beginning. I think the technology definitions there. And oh, Tafara answered the question. There you go. Thank you. Community sourced. Will, your question is, what is the RSOC and DOD of the battery module? If you mean reserve SOC, that's user configurable. There are various low-end thresholds. First threshold is the reserve as defined by the consumer, because it is consumer-owned equipment. They have a slider that's available for them to control how far it discharges to the first stopping point. And then below that, based on the total capacity of the system, there's a minimum reserve. And then below that are critical reserve levels where maintenance charge would step in. And then even further below that, if that maintenance charge, something was to fail, the battery BMSs have their own thresholds where they would go into hibernation. DOD, depth of discharge of the battery modules, is technically stated as 100%, but because of battery health maintenance routines, the depth of discharge is limited to, I believe, around 95% maximum. So that's that. Who's the manufacturer of the LFP cells? The LFP cell, the LFP modules are manufactured by Pylon Tech. Thank you for your question, Will. And then Andra, oversizing is for the DC panels, right? Or for the solar inverter. When you talk about oversizing as it relates to PV, like overdriving a string inverter, that is one way of oversizing an array as compared to a string inverter, a string PV inverter. So you can do that. That's called overdriving or oversizing the DC array for an AC PV inverter. And then as far as, so that's for that explanation, which is I think what you're getting at. As far as oversizing when you're sizing an AC nameplate rating of the battery system in comparison to the battery system, you don't want to crucially oversize the AC nameplate of the PV generation compared to the battery inverter. As I mentioned earlier in the presentation, because when you go to off-grid mode, you don't want that PV to overdrive the battery inverter and to trip it offline. The details of that are covered in depth in the Evolve Hub manual. So I recommend that you take a look at that. And if you've got any other questions after that, you can feel free to send me an email. Again, my email is shown on the screen now. Thank you for your question, Andra. Will, how does the round trip efficiency of the AC coupled system compare to a DC coupled system? Of course, because there's dual conversion, question sort of belies the answer. I think you can probably guess that the round trip efficiency of an AC coupled system, if you're going through multiple conversion steps, is going to be slightly less when you look at it overall, but it's only a difference of a couple percentage points. Parker does, thank you, Will, again, for that question. And the efficiency is listed on the spec sheet. So you can go to our product webpage and see exactly what that efficiency rating is. Parker, does that additional wiring need to be purchased or is it not included? Is it included? Additional wiring is not included. The wiring for the CTs, again, comes with a standard. Let me pull up that slide here. Right here. In addition to the AC power conductors, which is a standard, balance of system costs, you've got to buy those conductors. The CTs that need to be wired come with an 8-foot pigtail, and that's again, if you can group everything close enough to where an 8-foot pigtail will reach everything that you need it to. If it doesn't, and if you do need to extend it, those CT wire extensions need to be purchased. As far as the AK1 relay connection, again, this cable, I believe it's maybe 15 to 20 feet long. It comes with each system, but if you install the hub as instructed in the manual directly to the left of the PCS panel, PCS cabinet, you will not have to extend that. So the only additional wiring that you may probably plan on is CT extension wires, and that you can get that specification from our installer resources package. I believe if Courtney can share that with you, it should be included in there as far as CT extension, and the specs are shown on there. Thank you for your question, Parker. Jel, or I hope I'm pronouncing your name right. Is it possible to parallel two systems with two PV inverters, two hubs, two evolves, and two backup electrical panels to supply 10 kW of backup loads? 10 kW total, yes. If you have two backup electrical panels, you would have 5 in each, and it would provide that total of 10 kW. But your question shows two backup electrical panels, and if that's your constraint, then yes, absolutely. You can put two systems in parallel onto one service panel. You'll just have to look at the bus rating of that main service panel in order to put two 40 amp interconnection breakers on there. And so that's just a, if you're looking at putting two parallel systems on one service panel, that service panel is probably already larger than 200 amps. So I think the rest of it is elementary. Yes, you can do that, and it's a fun project to do. Tafara, thank you, Joe, for your question. Tafara, what max continuous discharge current C rating? The battery and battery inverter are sold separately. Where can we get pricing and stock availability information? Okay, few questions here, few different answers. Max continuous discharge current. For the AC current, continuous is 20.8 amps. The C rating of the batteries is a 0.5 C rating, which if you know what that means, then you'll know that will limit the battery's surge rating when in off-grid mode. So a 14 kWh based system will have a C rating, 0.5 C rating of 7 kW. So that 5 kW inverter, which would surge to 6 kW or kVA and for 30 minutes would still do that, but instead of surging up to 8.5 kVA for 5 seconds, it'll surge up to a max of 7 kVA for up to 5 seconds based on that C rating of a 14 kWh system. In order to get the full surge capability of the system in backup mode or 8.5 kVA, your capacity based on the 0.5 C rating needs to be at least 17 kWh. And so an extension cabinet can be added on in order to achieve that. As far as the battery and battery inverter, no, they are sold as one complete system. It is an AC coupled battery energy storage system, and the inverter and battery cabinets are UL listed as an integrated platform. As far as pricing and stock availability information, you can reach out to any of our sales staff. Courtney will be glad to help you with that. And then from Will, and thank you for your question, Tafara. I hope I answered it in its entirety. Will, one last question. Do these systems require yearly maintenance, preventive maintenance? That's a great question. As far as standard maintenance, I come from a pretty diverse background of commercial and utility scale, PV installations, as well as product development, engineering. And so I've seen everything from, multi-megawatt solar farms down to residential, battery system installations. When you're talking about yearly maintenance as required to maintain warranty, there's nothing that's stated in the warranty for that. So required yearly or preventative maintenance, nothing is listed in the warranty. But if you want to be ahead of the game, which it sounds like you already have that mindset, depending on the environment where you've got the system installed, some of the only things that would warrant maybe a closer look is the inlet fan covers on the bottom of the PCS cabinet. I would just basically look at that to make sure that the airflow is not interrupted. And that's really the main one. Make sure that the fans are still running when necessary and that airflow is not interrupted. Great question, by the way. Luke Harrison, welcome, Luke. How are you? I might add that using gutters and oversizing nipples in the installation will simplify wiring and look a lot cleaner. Absolutely. Thank you, Luke. Let me pull up. I have an example of an installation that I was going to show that I didn't pull up yet. This is a great example and speaks to what you just said, Luke, and I appreciate that input. Here's a quick picture of an ESS installation, a simple base system. This is the ESS where the cabinets are the same size. The LFP battery cabinet would just be slightly taller, the one on the right. What Luke is talking about here is the gutter and oversizing the nipples in the installation. So these kind of oversized conduit runs. You could probably do the one back and forth to the battery cabinet into the gutter with one larger size conduit. And then that way you've got this entire gutter to do all of your back and forth wiring with. And then you'd have one home run conduit effectively over to the main service panel. And that's exactly what Luke's talking about here. Thanks again, Luke. Appreciate that comment. That's a great point. Will, who performs the maintenance? That would be you as the installer. If you'd like to, or you can instruct the homeowner to, as customer-owned equipment, if they've got an agreement with you to do the maintenance, that's something that you can negotiate, or that might be something that you can cover with the customer as care of their home appliance, which this effectively is. So this is a home appliance. That customer, just the same way they would empty out the lint screen in their dryer, you might instruct them to, maybe every few months, take a look and make sure that that air inlet vent on the bottom of the battery cabinet is not covered. Great question, Will. Thank you. Tafar, I'm fully answered and greatly benefiting from others' questions too. Thank you. Okay, great. Awesome. Courtney, please reach out with any sales related questions. There's Courtney's information on the chat window there. Seems like we've gotten to the end of the chat questions. Again, thank you all for joining us today. Give it maybe another minute if somebody wants to shoot another question over here. But if not, again, Courtney's email is listed here for sales related questions. And if you've got any technical questions you'd like to email me, my email is located on the screen right there in front of you. So, and Courtney will let everybody know once the recorded session is available, and we'll email that out when it's available. So thanks again, everyone. Courtney, I'll hand it back over to you. And thanks again.
Thanks everyone for attending. I'll send out the recording later today. And again, as Jay said, if you have any more questions, please reach out to either one of us. Thank you.